Welcome to my talk. Thank you for being here. My name is Alberto Garcia. I work for Igalia. I'm a developer also, and I'm currently working on SteamOS. In the past, I've been working on other projects like Maemo Amigo, and more recently QEMU. So what I'm presenting here is a tool called Dirlock. It's a tool to manage disk encryption, but it is not a new encryption system. So this tool manages existing encryption technologies. So the reason why this started, the use case is due to my work in SteamOS. SteamOS, as you know, is the operating system for the Steam Deck and other devices that are also shipping it. And what you see here is what the disk looks like. We have immutable root file system. We have an AV update system, so we have 2 copies of the root file system. And we try to keep everything, all partitions very small, minus this large one that you have here, that is the home file system that contains everything, because games are very large, and we want to give as much space for that as possible. So we also put some things in the home file system, apart from the home directory, that don't typically go there, but they are too large to fit in other partitions. So this tool is designed for the goals of SteamOS, but it's also written in a way that is independent from the OS, so it should work in any Linux system. So the goals that we have in mind are the most important one, which is also the most basic one, but it's, especially in this case, we're thinking about a portable device that is easy to lose. So if you lose your device, your files should be unreadable. That's really the main use case. This is a basic one, but that's the one that we really care about. So at least the home directory should be encrypted. It would also be nice to have the possibility to encrypt other things outside of the home directory. Also, this machine has removable drives. Has an SD card slot, etc. So we would like to have the option to be able to encrypt things there. Although the operating system is currently single user, we also don't want to close the door to having multiple user accounts with independent encryption keys, although that's not in the plan at the moment. And of course, access should be authenticated. That means that the user, when they want to use the device, they need to enter some PIN, password, or something similar. But not all computers have a keyboard. In this case, we're talking about a computer only with a touch screen. So the expectation is that users are going to have very weak pins or passwords, so nothing that is with a lot of entropy. So it would be nice to have support from hardware-backed mechanisms to strengthen the encryption. Also, the Steam Deck has been in the market for a few years, and people are already using it. There's millions of users. It would be nice to enable encryption without having to reinstall everything from scratch. So ideally, we would like to have a button that says, encrypt your device. The device is encrypted, and then you can continue using it as usual without any major changes. And for management, we will need a higher level API, so DBus or something like that. And last, encryption always adds some overhead, but let's try to find a reasonable alternative. So let's try to avoid the encryption mechanisms that are too slow. So having a look at the existing encryption technologies, there's this category that is the stack file system encryption that is already discarded due to the performance, for example. This one, you probably know this project, gocryptfs, EncFs. Basically, you store your sensitive data as regular files in your hard drive. The contents are encrypted. And then you use a fuse based file system to mount it and to have access to those files. This is already available, actually, on the Steam Deck and the desktop mode. The Plasma desktop has this feature called the Plasma Vaults, where you can create a directory for your sensitive files. You can lock it with a password, and then you can unlock it when you need it, unlock it when you don't need it. This is very easy to use, and it works very nice, but it's not a good solution for encrypting everything. So the 2 realistic alternatives that we have is block device encryption, which in the case of Linux means LUKS, or native file system encryption, which is fscrypt. So we had to decide between these 2. In the case of LUKS, it offers the maximum confidentiality and protection because you have an opaque volume and you don't know what's inside. It also supports multiple authentication mechanisms. Systemd, with Systemd, you can have support for TPM and FIDO tokens. But it's a bit less flexible in the sense that you have to encrypt the whole device, or the whole volume at least. So depending on how you do it, usually you need to unlock it early on boot, which limits a bit the kind of authentication options or input methods that you can offer. It depends on the case. That's not always necessarily the case. In the case of this Steam Deck, it's almost certainly the case. You also don't have fine control about what to encrypt. You encrypt everything or nothing, like the whole device, not the machine, but the whole file system or something. And it's also hard to encrypt existing installation. Typically, you need to create a new block device, format it with looks, and then put the data inside. fscrypt, on the other hand, is very flexible in the sense that you can have an existing file system with your data, enable encryption, and start to put encrypted data there. It also allows very easily multiple user accounts and multiple directories with different keys. That's not a problem. It's very easy to integrate with PAM, and it's also very easy to unlock after booting the machine, like with also remotely with SSH, etc. On the negative side, it doesn't offer as much confidentiality as block device encryption. So although the file names and the contents are not visible, they are protected. The information, the metadata, the information that is in the inode is actually visible. So you can see the file sizes, permissions, timestamps, etc. So those things are visible. So for example, if you know in advance what kind of data you're going to store, you can guess some things about the data that is there. In the case of Steam, for example, the structure of the .steam directory is well known. So an attacker could guess, without unlocking the data, can guess how many games you have, even what games they are due to the size and the number of files, etc. So that's things that are sort of visible. It is also, fscrypt is an API that is generic and it's independent from the file system, but each specific file system needs to implement it. So at the moment, it's only supported by a few of them. But luckily, we use ext4, and ext4 is supported. And also, attackers can delete files. The files themselves are hidden in the sense that you cannot see the contents, but you can, with a normal unlinked system call, you can delete them. All things considered, we decided that fscrypt was a good alternative for our use case. It offers the good confidentiality guarantees. It's flexible, it's very easy to enable in existing installations, and offers good performance. In my tests, it's actually a bit faster than looks. But fscrypt is just the kernel API. So the way it works is that you give the kernel an encryption key, and the kernel takes care of protecting your files. But you are responsible, you meaning user space, is responsible for keeping that key safe and store it somewhere safe. So for that, the API doesn't concern itself about that. You are supposed to take care of it, and you're free basically to do it. So there are some tools to do it. One of them is the command line application called fscrypt, which is a bit confusing because it has the same name as the kernel API, but it's really a different project. So you can use the kernel API without using this tool or any of the file formats or anything that this tool is using. And an example of that is systemd that I'm going to talk about in a minute. So the fscrypt command line tool is the reference tool to manage encrypted directories. It was written in Go by two Google engineers, Joe Rich and Eric Biggers. They are also the people behind the kernel API. It's very simple to use. It covers all the basic functionalities of the fscrypt API, has PAM support, so you can use it to lock your accounts. But it only has basic functionalities, like you can use normal passwords and raw binary keys, but there's nothing else more fancy. There's also no DBoss API or anything like that. And then there's systemd. This is a kind of a different thing, because this is primarily not an encryption tool. This is a tool to manage human user accounts, as opposed to the user accounts used by system services and that. So the idea is that user accounts are portable, and the goal is to be able to move them from one computer to the other, etc. So for that, it offers various storage backends, and two of them are encrypted. One of them uses looks, and the way it works is that you create a loopback file, you format it with looks, and then inside of that loopback file, you put the file system. And it also supports fscrypt, although unfortunately only the old and deprecated version 1 of the API, which has some limitations. But in principle, it should be doable to update it to support the version 2 of the API. It also supports DBoss, PAM, and FIDO, although not TPM. This was a strong candidate, but there was a few concerns. Like primarily, it's not an encryption tool. It encrypts home and nothing else. Which is none of this is a blocker. None of these are blockers, but there were a bit of hurdles, I guess, in the way. For example, one problem is that there was a talk by Leonard this morning talking about the ID map mounts and how the current status quo is horrible. And his vision, I suppose the vision of the systemd project is to have something that is much better, but we are using the current status quo, and we would have a bit of troubles to convert everything. Also, another thing that is looks a bit more trivial is that systemd has its own user database, doesn't have the regular Unix users in etc passwd. So it diverts a bit from the typical way Unix systems are working, this looks like something stupid, but we have an operating system that is for running games, and games are complicated. We have some very old binaries that have bugs, that they do weird things, they don't always use the system APIs correctly, etc. And we have reports of several games, some are popular as Civilization 6, for example, that crash if the user account that is running the process is not found in the etc passwd file. Those things can be sorted out, and there are workarounds for these things, but these are the kind of issues that we were a bit concerned about, having something that is a bit different from the typical Unix system, and also has strong opinions about how the system should work, was something that was a bit worrying for our case. So we decided to create a new tool that uses the fscrypt API directly, and it's called Dirlock. So Dirlock does encryption, authentication, and nothing else. Doesn't touch anything else from the system, and it tries to be as least intrusive as possible. It's heavily inspired by the fscrypt command line tool that I mentioned earlier, and we actually tried not to divert from the design decisions that they made where possible. Also thinking in possible ways to maybe have interoperability, like convert the metadata from one tool to the other, or things like that. It's still under development, it's not production ready, but it's working. The PAM support is working, FIDO support is working. We have basic TPM support working. We use TPM basically as an anti-brute force attack mechanism at the moment. As I said earlier, we expect users to have very weak passwords, so TPM offers a protection mechanism that if you try to brute force a password, it will lock you out after a number of attempts. So that's what we're doing at the moment. There's also a dbus API, although it's in prototype stage, so not really usable yet. The code is free software, is our BSD license. It's published in the SteamOS GitLab instance. It's written from scratch in Rust. It works in any Linux system. There's nothing specific about SteamOS in it. If you are using SteamOS, it's already pre-installed in the 3.8 preview releases. Although it's opt-in, it's experimental, you have to enable it manually, etc. In the wiki, there's information about how to do it. So the basic architecture, comes from fscrypt. In fscrypt, one directory has an encryption policy. The encryption policy is a master key plus some other parameters, like the specific encryption algorithms. So you load the master key into the kernel to unlock the files, so you can see them and use them normally, and you remove the key from the kernel to lock the files. So, as I said earlier, you need the user space tool is completely responsible for managing that master key. So what we do is we don't use the master key directly. We protect it with intermediate keys called protectors. We have different types of protectors depending on the method that you use to unlock them. There's password, FIDO, TPM at the moment. This offers flexibility, and it also allows that if the protector is compromised, you can get rid of it without exposing the master key. This is the basic design taken from the fscrypt command line tool, but this is the same idea, has been used for decades, and Lux and BitLocker have the same thing. In Lux, the header has several slots, and each one of them can be unlocked using a different mechanism. So with the case of systemd, it has support for, as I said, FIDO, PCS, etc. BitLocker has the same idea. The implementation, of course, is a bit, there are some differences in the details, but the general idea is the same. In fscrypt, in Dirlock, we don't have one master key. We have one master key per directory, so we can have a bit more sophisticated scenarios, like, for example, two user accounts protected with two independent passwords, and then there's an additional protector that can unlock both of them, or two user accounts encrypted with two different passwords, and then there's a third shared directory that both users can unlock without having to share the password with the other user. These kind of things are possible. The basic commands are very simple. You basically encrypt a directory, and then you can lock it and unlock it when you want to use it. You can create new protectors and attach them to each one of the policies from each directory. And I will show a demo in a few minutes. And then we have PAM integration. There's a module called PAM Dirlock. And this should work with any type of user database or anything. Like the way it works is that when you try to authenticate, if the home directory of the user is encrypted by Dirlock, then this module takes control of the authentication and authenticates the user. Otherwise, it returns user unknown, and the next module takes control. And this is the same for changing passwords. So you want to change the password with the regular passwd command. It's the same thing. If the user is encrypted by Dirlock, then the module takes control. Otherwise, passes control to the next password. This means that when you enable Dirlock, passwords of the user are handled by Dirlock. So typically, the etc shadow database is no longer necessary for that user. But if you want, depending on how you configure PAM, you can also keep the password there and keep them in sync. So every time you change the password, it's changed in both sides. So both options are possible. And now we'll show a quick demo. I have a video recorded. This is a VM. This is a normal Debian. This is not SteamOS. And has a user account called guest that is unencrypted. This is like you can see the contents. If you run Dirlock status, that is not encrypted. So we're going to encrypt it now with a TPM protector. This virtual machine has a TPM. So once we encrypt it, we need to enter the PIN that we're going to use to unlock the account. And now the account is encrypted. The contents are still unlocked, so you can still see them. But once you lock them, this is what you see. Now the files are no longer visible, and if you try to open one of them, then you get an error. Key not available. So we can unlock it using the unlocker with PAM. In this example, I'm going to enter the PIN incorrectly a few times. So you can see what I said earlier, the anti-hammering mechanism. It keeps track of how many failed authentication attempts you have made, and you can see that those there. So. And now I'm going to create a new protector. This machine has a FIDO token connected. It's like a YubiKey. We're going to list it like this. So we can create a YubiKey, FIDO protector for the YubiKey, and we can create it so you don't need to enter any PIN or anything when you want to use it. So only with physically touching the token, you can unlock the account. So the use PIN false. You need to, when you register in the credential, you have to touch the device physically the first time. And now that the protector is created, you can attach it to the encryption policy used by the home directory. So you enter the name of the policy, the name of the new protector, and then you need to enter the unlock existing protector to be able to add the new one. So this is what we're going to do now. And now we have a encryption policy with two protectors available. You can see those there. One is the TPM protector, and the other is the FIDO protector. So if we go to the GDM login screen, when we try to log in, we get the message, confirm presence of the FIDO token. So if we physically touch the YubiKey, we will be able to log in normally. And now, if I log out, I'm going to remove the YubiKey from the system. This is a VM, so I don't need to even unplug it. I can just remove it from the VM directly, so from the QEMU monitor. So now if I check if there's something connected, it will tell that there's nothing. So if I try to log in, the system detects that there's no token anymore, so I need to enter the PIN normally. And that's basically how it works. So thank you. Have questions, comments, anything?
Thanks, very interesting. Maybe I missed that part, but could you elaborate a little bit more about the difference between your tool and the fscrypt binary? Like, why was it not an option to enhance that? And secondly, is it possible to chain these protectors in a way that it's not an or but an and, so enforce both TPM and YubiKey?
Yeah, so the first question is why not the basic fscrypt binary? Well, the reason is that it only allows passwords, basically, and there's no management API on top or anything like that. So one option would be to sort of fork the project and add those features on top, but I think like in the end, what we are doing here is just using the API of the kernel. It's not a lot of work. We're just adding new protectors. It's not a. So I also wanted to have the flexibility to evolve the project depending on the needs of the Steam Deck. So that's the main reason. Otherwise, the fscrypt binary works well. And the second question was I forgot. Sorry. Chaining protectors instead of an or and. That hasn't been considered. I suppose that's perfectly possible if I can think of a use case. I wanted to think about how to do it because the way the keys are related to each other, but it's not in the roadmap. But if there's a good use case, I can consider that, of course. I suppose I could create a new protector that is a combination of two others, or I don't know.
The protectors, where are they stored? Are they stored in somewhere else in the system?
Yeah, they're stored on disk on var, leaf, Dirlock, etc.
And is there a possibility to have these protectors stored somewhere that is shared between machines, so we can, for example, protect home directories and publicly available systems like in a library or so?
In principle, yes. There's nothing at the moment. The location is static, so to say, and there's nothing considered about that. But yeah, like especially if we want to start encrypting, for example, removable drives, we should store the protectors there for those drives at least. So, which is actually what the fscrypt tool does. But at the moment, there's no plan for that yet. That hasn't been decided.
I mean, with network file systems such as fscrypt, which supports fscrypt, so this would be a good thing to have.
Yeah.
I wonder, is there any chance this will work with ButterFS in future?
With ButterFS, I believe that in ButterFS they are adding support for fscrypt. I don't know because I've seen patches in the kernel, but I don't know what the status. I think it's not enabled yet. The tool is anyway independent from it. We use the API, so whatever file system implements it, we are fine with it.
Two questions. One, I assume that this was like some Fuse-based thing, sort of like encryptfs work. But you mentioned that the kernel has the secrets, yes?
The kernel has the encryptfs, which is also, it works like gocryptfs, but it's in kernel space. But that one is unmaintained and it's deprecated, and they plan to remove it.
Are you doing like an overmount of the home directory when you want?
No.
So it's all in the kernel? It's
all in the kernel. You add there's an IOCTL, you add the key to the kernel, and suddenly the files are visible.
That's super cool. And then the second question, do you plan integration like with systemd homed for this?
I think the projects have different goals, so I'm not sure. I think systemd homed could benefit from having the new fscrypt API, but I think really the projects have different goals. I don't know how that will work. Also, I think that the systemd homed prefers and recommends the Lux backend, which for us was not really an option in this case, I think.
When using the TPM protection mode, how do you store this in the PCRs, and how is this in the end protected if you, e.g., invalidate like some measurements because there was tampering with the hardware or something? Is this something you have to take into account?
So we don't use the PCRs at the moment. So we use only the TPM, like we use the ping for authentication, but the PCRs, like there's two ways to authenticate a secret in the PCM. One of them, with the TPM, one of them is with a ping or password, and the other is with authentication policies that allow more sophisticated mechanisms. One of them is this PCR register. We don't use them at the moment. If we add them in the future, the idea is that each one of these encrypted directories will have a recovery key that you can enter in case you lose access to the machine or something, and you can create new protectors, which is also the way BitLocker works, for example.
Just a piece of feedback, like getting the idea working, and you put some stuff in the kernel and it's all nice, but the amount of integration and like with PAM and everything and the tooling and the FIDO, like this is super cool stuff. Like it's awesome how well it works from looking at the demo. That was really impressive.
Thanks. It was actually not a lot of work. Like the PAM thing is really simple, but yeah, thanks.
So how close are we to, say, like GNOME onboarding experience where I actually have that little setup wizard at the beginning of the process and can tie something like a YubiKey into this?
In GNOME?
Yeah. I don't know if you know.
I believe that GNOME already uses or is gearing towards systemd Home-D, and they already have YubiKey support. So that should work already.
Well, thank you.